Good afternoon. Can you hear me?
Good afternoon, sir.
So, see, now we are be having regular classes, right? Your exams are over. Okay, so please make it a point to join. These topics will not be repeated. We have completed the dual nature of light chapter. We will do a few numericals today. Okay, so that you know we are on track on this one, and then we will move on to the next topic in the next class, okay, which is atoms. Okay, so let's get started. The numericals are really simple here. थोड़ा बहुत कैलकुलेशन ज़्यादा होता है, ठीक है, लेकिन उसके अलावा the concepts are very easy. So let's get started. The formula that we need to really use the most, right, is equal to K max is equal to H nu minus the work function. Okay. This is the maximum kinetic energy of the electron which is emitted. This is um, the nu is the frequency of the incident light, H is the Planck's constant, phi is the work function of the metal surface. Okay, the same thing we need to be able to articulate in different ways. For example, K max we should also know is also equal to EV naught, where V naught is stopping potential. Right?
Sir.
Hello?
Sir, am I audible?
Yes.
Yes, sir. Can you please explain determination of Planck's constant and work function?
You want to understand what about Planck's constant?
Yes, sir.
हाँ, अपनी प्लैंक कांस्टेंट में आपको क्या समझना है कि क्या होता है प्लैंक्स कांस्टेंट और वर्क फंक्शन, राइट?
Right.
Okay. See, what the Planck's constant essentially is the, see, when Max Planck was working with the spectrum, right, of, I think he was working on the spectrum of sodium at that time, and he was not able to find the difference, find relate it to the incident frequency, right? And to relate the energy to the incident frequency, okay, he used a constant called H. Okay, now this constant is known as the Planck's constant, and when Einstein used it, so there is no as such definition for the constant. It is just a constant of proportionality, because what Einstein found was that the energy of one photon, right, is proportional to the frequency, and the constant of proportionality is H. Okay, so energy of a photon is equal to H nu, where nu is the frequency in hertz. Okay, so this is the value of the Planck's constant is roughly 6.63 into 10 raised to power minus 34 joule second. Okay, so this is the Planck's constant. Now, what is the work function? Work function is the minimum energy that an electron needs to escape the metal surface. right? This is the work function. Now, if you look at this equation, which is the Einstein's equation, when we know all this, it's very easy to understand, because this is the energy that is given to the electron by the photon. This is the energy of the photon. When photon strikes the electron, it gives its entire energy to the electron. So this becomes the energy of the electron. And this phi, the work function, was the energy that the electron needed to leave the matter surface, the minimum energy. Okay, so this is the energy needed to break the bond with the metal. So what is the remaining energy? That is K max. Yeah, Deepika?
Yeah, sir. What about the graph V naught versus mu?
The V naught versus V graph, right? So what is the V naught versus V graph? Okay, so if we look at the V naught versus V graph, right? V naught versus nu. Okay, nu is the frequency. Okay, frequency of the photon, and this is the stopping potential. Okay, this is the potential we have given in the reverse direction to stop the current. Okay, now the graph for this is that it is zero. The stopping potential is zero till a certain point, till a certain frequency. Why? Because when the frequency is less than the work function, when the h nu is less than the work function, obviously there is no electron emitted at all. This is the minimum energy needed. So till that point, there is no electron emitted. So there is no energy needed to stop it, no potential needed to stop it. But once the frequency is above that, then the graph is a linear graph like this, which is evident from this equation also. Why? Because what is K max? It is same as EV naught. If K max is EV naught, what does this equation transform into? EV naught is equal to h nu minus phi. So it is a linear equation. This is a constant. So what do we find? That V naught is linearly dependent on nu. So we keep increasing the nu, the V naught required to stop the electrons keep increasing. Understood?
Yeah, sir.
Okay. So the key formula, right, in this to remember is K max is equal to h nu minus phi, and we should also know that the K max itself is equal to E into stopping potential. E is the charge on an electron. Okay. Another thing that we should also remember is that work function is equal to h nu naught, where nu naught is the threshold frequency, which is this frequency. Okay, this frequency is nu naught, so work function is h nu naught. Okay, so these are roughly the only formula that we need to solve numericals in this chapter. So this is one of the easiest chapters when it comes to solving the numericals. लेकिन ये कठिन है चैप्टर समझने के लिए. ठीक है, तो आप वो वीडियोस भी देख सकते हैं जिनकी क्लासेस अगर मिस हो गई थी, वो वीडियो देख सकते हैं, वो ऑनलाइन है वीडियोस. और उसके अलावा जो है, अगर आप वो चैप्टर बुक में भी, ये वैसे ये काफी अच्छे से एक्सप्लेन्ड चैप्टर है, आप बुक में भी एक दो बार इसको रीड करिए. ठीक है, न्यूमेरिकल्स अभी हम करेंगे तो आप देखेंगे कि बहुत ही आसान है. ठीक है, तो चलिए एक बार मैं थोड़ा सा यहाँ पे स्पेस क्रिएट कर लेता हूँ ताकि वी कैन डू द न्यूमेरिकल. Okay, so we need to find the maximum frequency for X-rays produced by 30K electron volt. Okay, there is a misprint here. 30K electron volt electrons. Okay, this is the unit of energy, right? So the energy is 30K electron volt. Now we have to find the maximum energy and the minimum wavelength for X-rays produced by these electrons. Okay, this has nothing to do with the photoelectric emission, right? Because X-rays are being produced by the uh, by the electrons, right? If you really look at it, that is nothing that we studied in this chapter, right? Then how do we do this question? ये चीज तो हमने इस चैप्टर में नहीं पढ़ी है, तो कैसे करेंगे? देखिए, हमने पढ़ा ये है जो आइंस्टीन का थियरी है, वो ये कहता है कि एनर्जी ऑफ अ फोटोन इज इक्वल टू एच न्यू. ठीक है, तो एनर्जी हमें पता है, एक इलेक्ट्रॉन अगर कोई एक्सरे प्रोड्यूस करेगा तो ज्यादा से ज्यादा अपनी पूरी एनर्जी दे देगा, उससे ज्यादा एनर्जी तो वो दे नहीं सकता है, राइट? तो द आंसर इज वेरी वेरी सिंपल, दैट द एनर्जी ऑफ एक्सरे प्रोड्यूस्ड विल बी 30K electron volt. If that is the case, then 30K electron volt should be equal to h nu max. This is the maximum energy possible. ठीक है, बस अब हमें जो है वैल्यूज डालने हैं. तो न्यू मैक्स जो है वो इक्वल होगा 30 इंटू के इज 10⁻³ एंड E is 1.6 into 10⁻⁻19 coulomb and volt, right, by h. Okay, h की roughly value होती है, this is the value we need to use if it is not provided. Okay, now this is the calculation that we have to perform. Usually the calculations are a little bit long in this chapter, right? So let's do that. Let's say 30 into 1.6 by 6.63 into 10 raised to the power 3 19 plus 2 into 24 to the power. This is 16, 18 hertz. Okay, this is the answer. Okay, the minimum wavelength of X-rays produced. अब हमें फ्रीक्वेंसी पता चल गई है न्यू मैक्स, तो वेवलेंथ कैसे निकालेंगे? वेवलेंथ और फ्रीक्वेंसी के बीच में क्या रिलेशन होता है? कैन समबडी टेल मी?
New lambda.
New lambda is equal to C. Very good, right? So lambda is equal to C by mu. Okay, so 3 into 10 raised to power 8 by 7.24 into 10 raised to power 8. So we get by 7.24 4. 0.0414 nano. Okay, so we prefer to give the answer in nanometer, although it's not a must, but wavelengths usually we tend to give in nanometers. Okay, so this is the answer. So this question only uses the concept that E is equal to H. Okay, let's do another question. The work function of cesium metal is 2.14 electron volt. When light of frequency 6 into 10 raised to the power 14 hertz is incident on the metal surface, photo emission of electrons occur. What is the maximum kinetic energy of emitted electrons? Right? Now this is the simplest possible question. Why? Because we know the formula straight away. K max is equal to h nu minus the work function. Right? So h is 6.63 into 10 raised to the power minus 34 into frequency in hertz minus the work function. Work function is 2.14 into 1.6 into 10 raised to the power minus 9. Okay, you know why I multiplied it with this, because it is electron volts. To convert it into joules, I have to multiply it by the charge on an electron. Okay, so this answer will be in joules because all the units are in SI unit. Okay, so we need to do this calculation. So now let's do that. 6.63 into 6 plus 39.78 minus 4. Okay, so this is the maximum energy. How will we find the stopping potential? Can somebody tell me where is the stopping potential here? Which relation will we use for a stopping potential? There are only 2-3 relations in this chapter. तो कौन सा use करेंगे?
V not E equal to
V naught E into V naught is equal to K max, right? So implies V naught is equal to K max by E, okay, which is 5.54 into 10 raised to the power minus 20 by 1.6 into 10 raised to the power. 6. Okay, so this is the stopping potential. Now let's do the third part. Maximum speed of emitted electron. How will we do that? How do we find the maximum speed? This is the standard, classical mv square. Half mv square is equal to kinetic energy, right? So what will we have? We will have v square is equal to 2 into kinetic energy by m. Okay, so we will find v square, which is 2 into kinetic energy, which is 5.54 into 10 raised to the power minus 20 m. M is the mass of the electron. It is an electron. The mass of the electron is 9.1 roughly into 10 raised to the power minus 31, right? So now we have to do this calculation, and it is 2 into 5.54 by 9.1 into 10 raised to the power plus 11. Okay. So V is equal to under root of this. Two into so we will use 3.48 into 10 raised to the power 5 meter per second. Okay, so this is the third part, which is the classical part, right? The classical physics that we know. There was nothing new in that. The photoelectric cutoff voltage in a certain experiment is 1.5 volt. What is the maximum kinetic energy of photoelectrons emitted? Okay, which relation will we use now? We know the maximum kinetic energy. No, we have to find the maximum kinetic energy when the cutoff voltage is given. So the relationship between the two is EV naught is equal to K max, right? So K max, either we can turn around and write the answer straight, right? In this unit, the answer is 1.5 electron volt, right? Because that is also an acceptable answer. But if we have to give the answer in SI units, then we have to multiply it by. So into 10 to the power minus 19 joules. Okay, so even this is a okay answer until and unless the units are specified in the question. Okay, monochromatic light of wavelength 632.8 nanometer is produced by a helium neon laser. Okay, the power emitted is, yeah. So in this question, we are given the wavelength and we are also given the total power. Okay, the wavelength is, the one which is of the wave as well as of the photon. This is the total power. Find the energy and the momentum of each photon. Okay, so energy, how will we find energy? We know energy is equal to h nu, right? Or it is equal to hc by lambda. Nu is c by lambda. Okay, here we will use this. So We will do that. 6.63 into 10 raised to the power minus 34 into 3 into 10 raised to the power 8 by 632.8 into 10 raised to the power minus 9, right? The important thing here is, I mean, you have to take care of the fact that it is nanometer, you know, all these units you have to be careful about. Okay, but the good news is usually the wavelength will be in nanometer, but please take care that the units are taken care of. Okay, now with this we will find the energy. Okay, let me leave this calculation out. You can perform it when you do the questions. Now let's just discuss how will we find the momentum from energy of of the photon, right? Now we have to find the momentum of the photon. How do we find the momentum of photon? Can somebody tell me that?
It would be 2E upon V.
Yeah, so we know that from, you know, we know that half mv square is equal to kinetic energy, right? We have to find mv from this, right? So it is mv square is equal to 2k, right? What we can do is multiply by m on both sides, right? And mv then will become under root 2km. This is what you said, right? Is that what you said? Okay, right? Now, this is what we use for any matter. Okay, this is what we use for any matter, be it electron, electron or alpha particles or an hydrogen atom moving something, right? This is the way we can find the momentum from the kinetic energy. But in case of the photon, right? In case of the photon, there is a small difference. And the difference is that the energy of the photon is mc square, not half mc square. Okay, so this is actually the K in case of photon, because we have to find the energy and momentum of the photon, right? This is the, so it is mc square is the energy. So to find, we multiply it by m on both sides is the way we could do it, but there is no m of the photon, right? So how do we find the momentum? So momentum in case of the photon is h by lambda. Okay, this is the momentum of a photon, right? This is what was postulated by Einstein. As a matter of fact, you can remember it from there, or you can also remember it from the de Broglie's. Okay, because de Broglie also used the same relationship that was postulated by Einstein, that a photon carries a momentum h by lambda. Okay, which is also equal to, okay, if you know the lambda, you can use this. Otherwise, it is equal to h nu by hc by h sorry, h nu by c, because lambda is c by nu. Okay, so in this case, we know h nu. So we will use this formula. Okay, so in case of photons, we will not be able to use this formula. We also don't know the mass there. You understood this point, that how will we find the momentum of a photon? Anybody has doubt? Remember that the momentum of a photon is h by lambda or h nu by c. This is a relation. We did it during the lecture. This you have to remember. Okay, so the momentum we will find as momentum is h nu. We have calculated the h nu here, and we will just divide it by 10 raised to the power 3 into 10 raised to the power. Okay, I'm not doing the calculation here. Okay, but this is the way to do the calculate the momentum. How many photons per second on the average arrive at a target irradiated by this beam? Okay, how many photons per second? Okay, now we will use the information about the power, right? We know this is the power 9.42 into 10 raised to the power minus 3 watts. So energy delivered per second is 9.42 into 10 raised to the power minus 3 joules per second, right? We need to find the number of photons. We divide it by the energy per photon. Okay, so to find the number of photons, we will use the energy per second by energy per photon, which is h, which we have just calculated here. We will divide that number, this number by this number. Okay, so energy per second, which is 9.42 into 10 to the power minus 3, and whatever is the energy of a photon we got here, we divide with that. We will get a huge number, you know, in 10 raised to the power 19, 10 raised to the power 20, that kind of a number we will get. Those many photons will be hitting the surface every second. How fast does a hydrogen atom have to travel in order to have the same momentum as that of the photon? Right? Now, this question, we will use what I think Deepika was saying at that time. We will use this formula. The momentum is 2k into m under root. Okay, you can remember this formula or you can work it out easily without taking much time. Okay, for this we have to use this formula. Okay, so we have some time. Let's try to complete this. If you have understood which we will use when, let's just try to complete this question. Okay, so let me just complete this for you. Okay, 6.63. So 3.14 into 10 raised to the power minus 19 joules. Okay, this is the first part. Now we will find the momentum. Momentum is 3.14 into 10 raised to the power minus 19. The energy divided by momentum is h nu by c. So 3 into 10 raised to the power, okay, so which is 1.05 roughly into 10 raised to the power minus 27. Okay, kg meter per second. Now let's do the B part. How many photons per second, right? So we know the energy, which is this 3.14 into 10 raised. Sorry, we know the energy per second, which is 9.42 into 10 raised to the power minus 3 divided by 3.14 into 10 raised to the power minus 90. Okay, this luckily is a very good number. We can cancel that. 3 into 10 raised to the power plus 60. Okay, 4. Right? Now we are